Okay, I don't think I ever properly introduced myself before, so maybe I'll do that now. So my name's Shane. I'm currently a third year medical student at U of A, and my background is in neuroscience and been interested in AI for a while. Just been trying to teach myself, doing some online courses, and also co-founded AIMS with the goal to AI is going to be a big component of medicine in the future, and I think it's important that our medical students now start learning about it, and that we build this community between medical professionals, students, and computing science students. And I'll plug our symposium now, which is on Friday and this coming Friday and Saturday, and we'll post the link again at the end. Okay, so today's lecture is all about assessing performance of your machine learning model. So last year, or not last year, last couple of lectures, we covered how to build a machine learning model, what are the components of it, what kind of things you need to think about when making one. And we talked about how to prepare your data to feed into your learning model, because of the adage garbage in, garbage out. If your data is a mess, if you don't clean it, if you don't organize it properly, then your machine learning model will never learn. So now that we've got our data, we've got our model, and we can feed the data into it and get something out, how do we know how well it's working? Is it training well? Is it performing well? How do you test it? So there's a few things we'll take a look at. We're going to assess training, performance, some ways to optimize, uh, some hyperparameters to play around with, and we'll mention a couple of other methods. So start with training. That's the main thing that your model does before it's ready to go, is to train it. And in our first lecture of the stream, we talked about loss. So loss is a summation of the errors that your model makes. The goal is to minimize the loss, minimize the total errors that your model makes. And it's a general measure of how well your model is performing during training. And often they're plotted on these learning curves, where it usually shows the training and validation loss. So the training, if you remember, is where the data we give it to train on, it will calculate how well it's assessing that. And then there's a subset of the data that we use for the validation. And if there can be sometimes you can get mismatch between how well it's doing with the training and with the validation. So this is a picture of a pretty much ideal learning curve. It shows the loss on the y-axis with a time or number of epochs on the x-axis. So every iteration of training it goes through, the loss decreases and gradually comes to a plateau. But what's nice about this curve is that training and the validation are very similar, and the loss comes down nice and low. As close to zero as possible is what we want. But it's very rare that you get this kind of nice, healthy learning curve, and instead you get other kinds of things. Now, this one's not too bad. This one is showing something called underfitting. And I think we talked about overfitting in the previous lecture, but underfitting is kind of the opposite, other side of the scale, where the model doesn't quite understand all of the data yet. And in this curve, you can see that the validation curve it's still going down a little bit. It's slowing down, but it's still going down. It hasn't quite plateaued. And that means it can still do more learning. And if you take a look at your learning curve and it's still going down, then you've got to give it some more epochs. You've got to give it more training. It'll take longer, but the more you train it, it should come down even better and come to and fit better. So that's one of the ways you can solve underfitting. And if you get something like this, on the other hand, where validation and training both kind of both converge, they're both kind of similar, which is always nice, but they've kind of plateaued in the middle. They're not coming down, the loss isn't coming down close to zero. What does that mean? That can happen if the data you have is more complex than the model you're using to evaluate it. And this is another kind of underfitting. It's not understanding the data properly. In the last example, it was just because you didn't give it enough time. But this time, it's come to this plateau. It's no longer decreasing. And so now that it's plateaued, you can train it, give it as many more epochs as you want. It's never going to improve unless you change something about the model itself. And so this could be something, one way of solving this is either maybe you're using a linear regression on something that needs a deep neural network. So you'd have to switch over to a different kind of model. Or if you're already using a neural network, maybe you need more layers or more nodes. It needs to be more complex to match the complexity of your data. So that's underfitting. And this is overfitting again. We talked about it before, but I'll talk about it again and again and again because it comes up all the time. This is where your model understands the training data way too well. It knows all the fine little irrelevant details of your data, and it's figured out some way to predict what is what based on the irrelevant idiosyncrasies of this particular data set. And when this happens, it does great on the training set, but it can't generalize to other similar data because it's basically memorized all the details. And if you look at a training on the learning curve, you'll often see that the validation loss is following the training loss for a little while, but then all of a sudden validation stops decreasing, starts increasing, training starts and continues to go down. The loss goes lower, 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 lower. So this is called divergence. The validation and training are diverging. And there's a lot of different ways to solve this. One of them could be kind of the opposite of underfitting, where your machine learning model is way too complex for the data and it's trying to find complexity where it doesn't really exist. And another way to solve this is something called early stopping. So if you follow the curve, you can just stop the training just before the validation starts going up again. So that'll give you an adequately trained model. And then the last thing you can do is adjust hyperparameters. I think we mentioned those before as well. Those are basically all the little variables you can adjust in your machine learning model to change how it trains, change the training rate, the number of epochs, batch size, things like that. We'll talk about that more in a little bit. So that's a simple way of assessing training. Now we're going to talk about how to assess how your model is actually performing. Now that you've trained the model, you've figured out how to train it, how is it actually performing? So we're going to start with the confusion matrix, and it's often very confusing to people. So I'll try and clarify as best as I can. It's actually very simple. It's just a lot of similar terms with the little differences. So this is a confusion matrix. And what it's showing is the true positives and the true negatives compared to the false positives and false negatives. So at the top here, we have your actual class. That means if you have a set of data and let's say half of them are, let's say a population of patients, half of them have liver failure and the other half don't. So the true positives will be all of those patients that have liver failure, and the true negatives would be all of those that don't. And on here is the predicted class. That's what your machine learning model is predicting. That you give it the list of patients and all their data, and it'll say whether it thinks they have liver failure or not. And when the prediction matches the actual, that's called the true positive. When the prediction misses the actual disease, that's a false negative, because it predicted it as negative, but it's actually positive. And then over here, you have the population that does not have the disease. And if your model predicts that it does have it, that's a false positive. And if the model predicts that it doesn't have it, and it actually doesn't, that's the true negatives. And if you work in research or familiar with statistics, false positives are also known as a type 1 error, and false negatives are type 2 error. So the red ones are the errors where it's made a mistake. So I hope that makes sense. There are a lot of different metrics we can get from this so-called confusion matrix, and if it doesn't make sense, it will as we go on. So some of these are called accuracy, precision, recall, F1 score, and ROC or ROC. And those all mean something to you a little bit later. So we'll start with the simplest, which is accuracy. It's basically what it sounds like. It's a measure of how accurate the model is when you apply it to real data. It'll tell that this is a formula for how to calculate it. It's the true positives plus the true negatives divided by the total. So everything it got right divided by all the possibilities. So if it got 80% right, then it's 80% accurate. But there's a big problem with accuracy when you have a class imbalance. For example, if you're building a machine learning model to detect schizophrenia in the population. Well, schizophrenia has a prevalence of about 1% in the general population. And if your model decides to classify every single person as normal, as not having schizophrenia, then it'll get 99% of it right. It's doing no better than just pressing the same label on everything, and it'll get 99% right. Just see, there's a question here. Is the confusion matrix based on validation data only? So this would be based on the test data. So once validation set is used during training, and then you'll have a separate test set of data that you'll use the trained model on. And that'll be where these values come from. Okay, so back to accuracy. Yeah, when you have class imbalance, when there's a very small population that's your target, then even with poor performance, it can have a good accuracy. So that's often not the best metric in medicine. So there are several others we can use. Okay, next one is precision, and it's also known as the positive predictive value. So what precision answers is, of all of the positives that it predicted, how many did it get right? How many are actually positive? When it says it's positive, how trustworthy is it? How precise is it? And you can calculate it this way with the total number of true positives divided by the total of true positives and false positives. So it'll be the true positives divided by the total predicted positives. For an example, if your precision is 0.74, that means that, let's say it said that 100 of your patients have this disease. Then if you have 0.74 precision, that means 74% or 74 of those 100 were correctly diagnosed, while 26% were misdiagnosed. So if we want optimal precision, that'll give us more correct positives. But often this is one of those things where you might be okay with a misdiagnosis if you're catching all of the correct diagnoses, because then you can sort that out later with you can add another further investigations to weed out the misdiagnoses. Okay, the next one is called recall, and this is also known as sensitivity. So this is how many of the true positives or how many of the actual positives did it find. So this is calculated by, you take the true positives and you divide it by the true positives over the plus the false negatives. So precision was looking at of all of the positives that were predicted, which are actual. Recall is looking at of all of the actual positives, which ones did it get right. And for example, here, if you have a recall of 0.82, then that means if you have 100 patients with the disease, then it'll find 82 of them, and it'll miss 18. So this one is something we want to pay attention to, especially in medical applications of AI, because you don't want to miss something that's treatable. If we go back to precision, it's okay to misdiagnose something, because this isn't going to be the final say. It's not going to have the final say often. But if you're missing them, then that can be a big problem. So recall is important. Another measure is called the F1 score. This is used when it's important to have both precision and recall high. There's often a trade-off between precision and recall. So for example, if 25% of the population is sick and you diagnose everyone as having the disease, then the accuracy will be 25%, because 25% actually have it. The recall will be 100%, because of all of the sick population, it's diagnosed all of them. But the precision will be 25%, because 75% of those are misdiagnoses. And example 2, if you diagnose only the 25% that are actually sick, then accuracy is 100%, because it got all of them right. Recall is 100%, got all of them right, no mistakes. Precision is 100%, got all of them right, no mistakes. And the third example, if you diagnose 5% of that actual 25%, then the precision will be 100%, because of all of the positives that it predicted are actually positive. It's precise. But the recall will be 20%, because it missed that portion of it. And then accuracy is 80%. So these all go up and down in different ways, and which one you want to focus on will depend a lot on your application, what exactly the machine learning model is trying to figure out. And in the case that you want both precision and recall high, this is where you use the F1 score. It's calculated like this. It's called the harmonic mean of precision and recall. It's basically two times the precision times the recall divided by the precision and the recall. And the F1 score decreases when either precision or recall are low, and it increases when both are high. So in these examples, F1 score here is 0.4, 0.33 here, and 1 here. So precision's low, this is going to go low. Precision's high, but recall's low, it's going to be low. Both are high, you get a high F1 score. And the last metric we'll look at is the ROC, or ROC curve. This stands for Receiver Operating Characteristic. And don't try to figure out how that's relevant to what it's actually doing. Its name comes from historical use in World War II, where radar receiver operators would use this to adjust their threshold of their radars. And how this works is it plots the true positives, the true positive rate. So this will be basically the percentage of true positives versus the false positive rate. And it does this for every given classification threshold. And if you remember from our first lecture, where we had these activation functions, if the output value is over 0.5, then it'll assign it a 1, or if it's less than that, it'll assign it a 0. And in this case, the threshold is 0.5. So you can fine tune this by telling it, oh, I want the threshold to be a little bit higher. Maybe have the cutoff point 0.9, or maybe I want it a little lower, make the cutoff point to be 0.1. And so the ROC curve will graph the true positive rate and versus the false positive rate for every point along every different threshold value. So for example, if your threshold is set it to 1, so way up here, then it's only going to give you a positive if it's 100% certain. And very few things in life are 100% certain. And so your true positives and false positive rate is probably going to be 0, close to 0. So that would be this corner down here. And if you set your threshold to 0, then it's going to say basically anything and everything is going to be positive. And the true positive rate and false positive rate are going to be over here at 1. And if everything is completely at chance, this ROC curve will be a straight diagonal line cutting from the bottom left corner up to the right hand corner. And as performance improves, the curve will bulge out closer and closer and closer to this corner here. And the way to measure that is by taking the area under the curve. So you calculate the area under the curve here, and the closer it gets to 1, the better of a metric this becomes. And on the other side of things, sometimes you can get the negative, and it gets closer and closer to 0. Now, what do you think if the area under the curve is 0, would that be a good thing or a bad thing? Any ideas? Does it make sense so far? So if the area under the curve is 0, then that could actually be a good thing, because it's like the straight line here will give us like a 0.5 value, where it's random, basically random. And if we have it 0, it's basically just the inverse of 1, in that it's getting everything backwards. It's correctly separating, correctly classifying, or it's not correctly classifying, but it's classifying everything, putting everything into classes. It's just got the labels backwards. So you can swap the label, just invert the labels, and it'll be good to go. Okay, so there's a question. Is having a high true positive rate and a high false positive rate a good thing or a bad thing? So a high true positive rate and a high false positive rate. So let's see. High true positive would be up here, and high false positive would be over here. So that would be a bad thing, because if true positive is high and false positive is high, it's basically labeling everything as positive, and it's not really discriminating between different classes. So ideally you want true positive rate to be high and false positive rate to be low. But you can also have a condition where the true positive rate is low and the false positive rate is high. And in that case, that's just where you have your labels. It's got the labels backwards. But that can still be a good thing. Okay, so those are some of the common metrics you can look at. And which one you used, again, depends on your problem, depends on the data you have. And you can look carefully at what kind of outcome you're looking at and which metric would apply the best. So now that you've got an idea of how well your model's doing, you can start trying to optimize it. And how do you do that? Number one, always start with your data. If there's a problem, always check your data. If you haven't checked it already, check it. If you have checked it already, double check it. If you've already double checked it, triple check it. Make sure everything is properly inspected, all the processing is done. Make sure there's nothing missing. Careful about outliers, and always start by looking at your data. And the other thing you can look at is the actual model that you're using. What do you need? Like a linear regression, a deep neural network, or something more advanced like a convolutional neural network? Those we'll talk about in the next lecture in this series. But the things that once you've looked at your data, the things that you can adjust are the hyperparameters. And we're going to look at a few common ones: the learning rate, regularization, epochs, batch size, threshold, and layer depth and width. So learning rate, we mentioned that before. This is basically how much to adjust the weights in your model. And the way to graph it is we're trying to find the global minimum of the loss. This is a graph of loss. And you can make big jumps to try and find it, or you can make small jumps to try and find it. If your jumps are way too high, you'll just jump around forever and never find the global minimum of your loss. And if it's too low, the steps will be so small that it just takes forever to get there. And you can use a constant learning rate, but that's quite rare nowadays. You can instead, there are adaptive learning algorithms that will take a look at how quickly the weights are changing and it'll adjust the learning rate based on that. And so that's called the learning rate decay. As it gets closer and closer to the minimal loss, it'll decay the learning rate. It'll slow it down so that it can fine tune where it is. And there's just listed three here. One's called stochastic gradient descent, another's called eta grad and atom. And I'm not going to talk about the math behind them, but you can always look them up on your own. You can use these if you're programming in Keras, making your own model. These are all ready to go. You just type in atom or eta grad, and it'll perform all the calculations automatically. And you can do some fine tuning of how quickly they adjust the rate decay. So those are a few things you can play around with for learning rate. Next are the epochs. So an epoch is one epoch will be a training session where the model trains on the entire set of training data. So the more epochs you have, the more times it goes through the set of data. And the more epochs you have, the longer it takes because you're computing more and more and more times. And this is the learning curve again, showing both underfitting, overfitting, and a good model. And if everything in your model is good, and you just need to adjust epochs, and you find that you're underfitting, then you just need to add more epochs, and it'll make it to the optimal training. But if you have too many and it starts diverging because it's overfitting, well, then it's already reached the optimal loss a while ago, and you probably have too many epochs, so you can stop it early. And another case where, let's say at this point you have 50 epochs, and let's say in your model you've put in 100, and at 50 it reaches this point. At 75 it's still at this point. At 100 it's still at this point. Then you just have that your model's doing well. You just have too many epochs in there, and you're just wasting time training. It's not learning anymore at that point, so you can cut it back. So ideally you want to have the fewest epochs possible, because that'll save you on computing time, which can be costly. Next thing you can adjust is the batch size. So the batch is the number of data points that are used before updating the model's weight. So in other words, within a certain epoch, let's say you have 100 data points. And in one epoch, your model has to go through all 100 of those data points. And the batch size, let's say you have the batch size set to 10. That means within one epoch, it's going to take 10 of those data points, run them through the model, and then update the weights. And it's going to do the next 10, run them through, and then update the weights. So it'll do that 10 times if you have a batch of 10 with 100 data points. You could set it to 1, and in that case, it's going to have to go through 100 times within one epoch. So if your batch is smaller, it'll update the weights more times in one epoch. If it's bigger, it'll update it fewer times in one epoch. And if your batch size is too small, then you can get good generalization in that, because it's only using one point of data at a time to update the weights, it's not seeing it doesn't really have a chance to overfit. So if something is well trained with small batch size, it often can be generalized. but it can take a very long time because it has to do so many more computations, and the training can be noisy and it can miss the global minimum because there's a lot of variability. It doesn't see the full picture all at once, so the weights can jump up and down a bit, and you might not get to the global minimum. If, on the other side of things, if your batch is too large, then it can be faster. But if your data set has 1 million parameters, then your computer might not have enough memory to hold like 500,000 in one calculation. So you have to consider what kind of computing power you have available to you and whether it can handle that batch size. And the benefit of a large batch size is that it trains a lot faster, but you do need that higher computing power. But there is a risk of overfitting because it's seeing a lot of data all at once. It can easily find patterns that aren't really there. So with all of these, there's no good rule like, oh, just put this as high as you can and then your model will work, or put it as low as you can, your model will work. It's all trying to figure out where in the middle is the optimum. And another thing you can adjust is the classification threshold, which I already talked about in the ROC curve. This is the ROC curve again. You can put it higher or lower depending on your purposes. And then regularization. This is a way to kind of minimize the kind of outliers in your model, a way to keep it under control in a sense. So there's common ones that are called L1, L2 regularization and dropout regularization. I think Amira mentioned these briefly in the last lecture. So L1, what that will do is it'll look at all the weights that have been updated in your model, and it'll put a penalty on the magnitude of the weight. So let's say if you look at all the nodes in your network, and this one is 0.5, this one's 0.2, this one is 0.4, this one's 0.8, and this one is 50. Well, that's weird. Why is it 50? Maybe it's looking at something. Maybe it's found something that it shouldn't be paying attention to. So this will put a penalty on that 50, and it'll kind of rein it in. It'll bring it down to a lower value to be more consistent with the range. And L2 is another kind. In this case, it'll penalize the square of the magnitude. So this one's a little bit more sensitive to deviations in the value of the weights. And there's two graphs here. On this one is an example of distribution of the weights within your model. This is one that has been regularized. Over here is another distribution of those weights that hasn't been well regularized. And there's more on the fringes. And there's a value you can adjust. Again, I haven't shown the formula. That's something you can look at on your own, but there's a value called lambda. It's a coefficient used in both the lasso and L1 and the L2. Yeah, the L1 is also called the lasso regularization. L2 is called ridge. And the lambda is a coefficient that can be adjusted to basically control the strength of the regularization. So if you make it really high, then it'll look more, your distribution of weights will look more like this. And if it's too high, you have a risk of underfitting. It might constrain the values so much that it never has a chance to learn. And if you make it too small, then you're not really regularizing much, and it'll look more like this. In this case, you have the risk of overfitting again. So you can adjust lambda to try and find the optimum value if you're using regularization. And then dropout, we talked about that before as well. This is another form of regularization where you randomly remove some nodes in your network for each epoch. And generally, it's best to choose a value between 0.5 and 0.9. Anything above 0.9 will risk underfitting because it just doesn't see enough data, and anything less than 0.5 will risk overfitting because it's seeing too much. And then lastly, there are more hyperparameters than this, but this is another one you can play around with. This layer depth and width primarily applies to neural networks. So you have your input layer, hidden layers, and the output layer. Generally, a good way to start is to make your first hidden layer equal to the number of input parameters, and the output layer equal to the number of classes. And as your data gets more and more complex, and if you see that it's underfitting, then you're going to need to add more layers. You can add more nodes in the layers. But how do you decide what you're going to do? How do you know how many layers to add? How do you know how many nodes to need? And nobody really has an answer for that. It's largely experimentation. If you have previous experience with similar data, you can use what worked before as a starting point. You can see what worked for others as a starting point, or you can just play around with it, see what works. It's a lot of trial and error in machine learning. And a couple of other methods. One's called meta learning, and there's like a little meta thing here. Any Nicolas Cage fans here? That's Nicolas Cage and the Nicolas Cage. Very meta. What meta learning is you use another machine learning model to assess your hyperparameters and optimize them. So you're applying machine learning to optimize machine learning. And you could use that to optimize machine learning, and so on and so on. Another option is called ensemble learning. This is where you have multiple different models that all give you an output that feed into what's called a generalizer, and then it gives you a prediction. So this is like getting second and third opinion. So those are main things you can do to assess performance and optimize. There any questions so far? I hope I didn't go too fast through it all. Okay, so we talked about assessing training, looking at the learning curves, looking for underfitting or overfitting. We talked about how to assess performance with the confusion matrix, the true positives, false positives, true negatives, false negatives, and you can get out accuracy, precision, recall, F1 score, ROC. Talked about how to optimize. Always start with the data. Always start with the data. And make sure your model is appropriate for the data. And then you can play around with all those hyperparameters such as learning rate, regularization, epochs, batch size, classification threshold, and the layer depth and width. And you can, not going into those in detail, but you can look into meta learning and ensemble learning as further ways to optimize your model's performance. Okay, and that is basics of assessing performance and optimizing your machine learning model. Any questions? Okay, so one question is if overfitting is all about looking at the smaller details, why would that necessarily be a bad thing? So it's not necessarily a bad thing, but the problem is when it's looking at the small details that are specific to your training set, and it'll find patterns in there that don't apply to the general population. And that's when we say it's overfit. It's basically it's found things, very specific things about that specific subset of all the data, and it's found some way to find a pattern that helps it predict it accurately, but it only applies to that training set. And so if you give it some other data, then those smaller details don't apply. And it really depends on what the details are and if the smaller details are relevant. So if I could use an example, let's say you're looking at sand dunes in the desert, and let's say there's 3 different types of sand dunes, and your machine learning model has figured out how to tell the difference of them based on the positions of each grain of sand in the dune. And that might be that's something that's very specific to each of those, and it's not a detail that will be generalizable to the other sand dunes. I don't know if that's a good example, but it's finding, when you overfit, it's finding detail that doesn't really have any effect on what the actual outcome is, but just by chance there's a pattern that it can find. Yes, that's a much better way of saying it. It makes assumptions based on irrelevant data. Yes. Okay. If there are no more questions, then I will remind everyone of our symposium on Friday and just post the link for you guys. If you haven't signed up now, there's still time. Okay, so there's 2 days to the symposium. Oh, it arrived. Great. So there's a pre-symposium, which is basically just a networking day. There's going to be some like speed networking, as a booth fair with different AI companies, startups, clubs, and then some breakout rooms just for everybody to get to know each other. And then on Saturday is going to be the main symposium with the speaker series. So you can attend one or the other or both. All right. I hope everybody learned something. Hope it wasn't too boring. It's a little bit of a dry topic. And yeah, see you at the symposium. Oh, and we have our next workshop on Wednesday. And yes, there is going to be a lecture after the symposium, but it will be at it's going to be later, I think, starting at 5 next weekend. So I'll send out an email about that. All right, thanks everyone.